Hello, geometry students. In this lesson, it's going to be pretty quick. It's probability of independent events. And I'm going to focus mostly on this formula that says if you have two events, A and B, if they are independent, then to find the probability of both of them happening together, it's just multiply them together. The classic on this one is flipping a coin and rolling a dice. If I flip a coin and it turns out to be heads, what's the probability that if I roll a dice that it's going to be an even number? Well, those two events are completely independent of each other. The occurrence of one does not influence at all in any way the occurrence of the other. They're completely independent. And if that's the case, to find the probability of happening in both at the same time, they can happen at the same time. The probability is just multiplying them together. The example I just gave you, what's the probability of heads and even? Well, the probability of heads is 1/2. The probability of even is also 1/2. Just multiply them together. Roll a dice, flip a coin. What's the probability it's going to show heads and even? You got a 1 in 4 chance of that happening. So on this one, this is just straightforward formula. If these events are independent, I'm determining whether these events are independent. To determine if they are independent, it must be true that the probability of A and B is equal to the probability of them multiplied separately. So that's all I really have to do. Take A, multiply it times B, and check to see if it's true that it equals the same thing as A and B. Well, just multiply them together. That does not equal. In fact, it's significantly off. Makes me wonder if I have a typo on that one. I'm going to do this one again. These are not even close. So these are definitely not independent. Not even close. That one surprised me. So look at the second one. The probability of K is 50%. Probability of L is 50%. Is that the same as the probability of K and L? That means intersection right there, which they're telling me is 25%. Well, this is 25%, and it is equal to 25%. So yes, these are independent. And incidentally, this is the example I just gave you. This is the probability of getting heads. This is the probability of getting an even number on a dice, and it is equal to 1/4. So it's just a test for independence. If it's true, then they in fact are independent. These obviously are not, because A and B must be influencing each other in some way. All right, well, on this one, I'm telling you that they are independent. So the formula is probability of A and B must be equal to the probability of A times the probability of B. I'm just going to fill this in. The probability of A and B, they tell me, is 0.14. The probability of A is 0.35, and I'm looking for the probability of B. Well, you just divide. And you find that the probability of B is 0.4. Be careful on this one. I don't really know what I'm supposed to do until I write the formula out. If I don't write the formula out, I'm not sure if I'm supposed to multiply or divide. If I end up with a number greater than 1, probably made a mistake. So here I'm going to write the formula out again. And I'm just going to fill in what I know. The probability of the intersection, both of them happening at the same time, is 1/6. The probability of, I guess I'll call this one K. And the probability of the other one. So again, you divide. And you find that the probability of L is equal to 8. Notice it's easy to get it upside down. You don't multiply them. You divide the wrong way. You can get the wrong answer on these. It's just basically plugging it into the formula. How about a more realistic example? The probability that a customer wants cream with their coffee, 40%. The probability that a customer wants sugar, 70%. The probability that the customer wants both A and B is 27%. Be careful about that. I think I'm going to write that out. Cream and sugar. And then I want to test to see if these are independent. I guess the first question would be, do they seem independent? Does it seem like somebody comes in, they say they want sugar. Are they more or less likely? Is it somehow influence the probability that they also want cream? I personally think that they probably are not independent. Meaning I think that if you want sugar, you're probably also the type that likely drinks cream also. But let's find out. The probability of A and B is 27. The probability of one of them is 4. The probability of the other one is 7. This is going to be very close. They are not equal. What's your conclusion? Well, that's kind of tough because this is obviously they need to be exact, but these are so close that there's no way you're ever going to get some exactness. So I think you can make the argument either way. But since in this case I'm proving the conclusion by saying they're not the same, then I can say they're probably not independent, even though I think they probably are. I said that backwards. All right, look at number 4. A student is chosen at random. Does this seem like they would be independent? If I tell you that a person's in the music club, could you just say, oh, that person must be male or female? Or the foreign language club. In other words, are males more likely to join than females, or females more likely? If there's any difference whatsoever, then they're not going to be independent. Knowing students, I'm thinking these are probably not independent, although they probably should be. So, probability of female, that's easy enough. That's 85 out of 161. In case you're not sure, I'm basically looking at this number, the total number of females, over the total number total. And I guess I'll figure out what that is. That's 52. How about probability of being in the musical club? Well, there are 70 students in the musical club. And that's 43. Next, I'm looking for the probability that you're in a female in the musical club. Well, I'm going to go and look for all the females in the musical club. That's what that 38 represents. 38 females who are in the musical club out of the total possibility. And that's 24. All right. Next, I just need to determine if these events are independent. My feeling is that they are probably not, but I don't need to wonder. I'm going to just fill it in. The probability of A and B I found was 24. The probability of A is 53. The probability of B is 43. This is close. So my conclusion is these are probably not independent. But I will also say this. These numbers are so close on this one and the last one that the conclusion really isn't certain by any means. But for us, we are going to say that these are not independent because these are not equal. And that's independent.